Welcome back to my class. So what we're going to do today, we are going to solve these problems, actual problem solving now. So these are word root questions. And they get kind of confusing because there's going to be a few different types. We got interest kind of questions. And then later on, we'll talk more about like exponential decay, exponential growth functions. And then next lesson after this, we're going to actually start learning how to use logarithms to solve these kind of questions. So let's see what we have here. So we are going to solve some word equations, and they do get a little bit weird, but this equation here, this little setup that we have here, a is equal to p times 1 plus I bracket n, is very similar to what we did before when we talked about the growth of a fish population, or decay of a fish population, and the growth of a bacteria culture or something. We talk about exponential growth functions. This 1 plus I is very similar to that. It doesn't always have to be plus I. If it's a decreasing function, you'd minus I, because you always want your C value to match what's happening. So if it's a compound interest and you're paying off something, or you're being charged interest, those will probably be growth functions. And then if your money is slowly decaying, like say the stock markets right now, that would probably be a decay function, because your money is decreasing over time. So let's think about how we can solve, how we use this. And here we have a couple of words in here, like A just stands for, because they don't have any other number or letter for it, how much money you have at the end of an investment. P is called the principal amount. How much do you start off with? Very similar to what you probably learned in comm class. I is the interest rate. And now the key to this is per compounding period, right? And N is the number of compounding periods. Now, this is, there are two ways you can kind of combine them together so that N is not necessarily always compounding periods. N is maybe just the amount of time in years or days or months or something like that. So you can combine them together as one thing, so you don't always have to talk about compounding periods. So if I do it that way, you may think of N being quarters. How many quarters have happened, or how many halves have happened, right? Or how many 15-year periods have happened, depending on what the compounding period happens to be. So let's see how that kind of relates to what we're doing here, and how the I is going to change from what you see here sometimes. Like this is per, like if I were to look at this first question here, I have an interest per year. How long does it take to do this? So it says per year, and the compounded quarterly. So that's going to be a bit weird. You want to know how much interest per quarter per compounding period. Okay. So to figure that one out, to find out what the actual I value is, because this is per year and this is quarterly, and quarterly happens every quarter of the year, so there's 4 quarters in a whole year, the amount of interest you're actually going to get is not 7.5 per year. You're actually going to get that number divided by 4 per quarter. So your interest is not 7.5, your interest is actually 1.75%, 1.875% per quarter. Right? That's how much you get per quarter. And that's actually pretty useful. It's actually better for the investor. The more times they quarter, or how many more times they compound the interest, the better for you. There's actually a lot of calculus behind that, how logarithms actually developed. They've actually developed upon these kind of interest calculations, and then shrinking down how much you actually cut the pieces in. Like we can redo this question and say, what if this was per month? How long will it take me to get to this, what he wants is $2,700. So he wants, in the end, he wants $2,700, oops, at the end. And we have an initial investment of $1,500. He wants to know how long does it take to get that to that amount, right? Now you can brute force this, and you can just keep on adding on that percentage. Oops, I'm gonna just pause my video. All right, so back at it here. So we have an A value, $2,700. He has the initial amount that he wants to put in here, $1,500, and this is gonna be compounded quarterly. Now there's two ways to set up this equation. So we can set up the equation. First of all, I'm just gonna put A here rather than the amount we're looking for here. So my initial amount, 1,500, and then we're gonna go 1 plus this percentage. So I'm gonna put that percentage into decimals. So we can just divide by 100 to get that percentage. And then we're going to raise this to a power. You just raise it to the power of n. And when you solve for n, that means that's how many quarters you've actually solved for. Right? Now, other ways to solve for this would be, just one second. Sorry. All right, so back out of here. So another way to do this, rather than just putting x here, we could do that. We could solve for x. Or we can do the same thing we did with the half-life formula. We go t over, change that, t p. Rather than half, you can think of it as compounding periods. Now, because t, I'll just put down here where t is in, let's say, years, my compounding period is quarterly. So it happens every quarter, a quarter of a year. So that's very important to know that. So if I did this formula with the t over p would end up being t over a quarter, because it's a quarter of a year for the period, so we put a quarter there. Now that can change to an exponent because it's divided by a fraction. I'll just add these two numbers together actually before we go any. Right, and the plus here. So because it's divided by a fraction, we can say that's t, 4t. And when we solve for t, we're actually solving for how many years, not how many quarters. We just put an x here instead, so, or n, so this will n here. If you just put an n there instead, you'd be solving for how many quarters are happening. And it's going to be a much larger number. You did the divide by 4 to get how many years it actually would be, because you don't want to know how many quarters. Because there's 4 quarters per year, you divide by 4. If you just put an n there. But if I did this way, I put a t here, then we could solve for t. All right, so we're going to go to our graphing calculator here, and we're going to solve for t. Now, you're going to see that once we graph this, okay, no, actually, let's just remove some stuff here and just zoom to a regular zoom here. Okay, so we're going to graph this. So we should probably put something that's equal to here. We want to know when this ends up being $2,700. Okay, so we're going to graph the 2,700. I'm just going to mention now, like if I graph right now, you're not going to see the line for 2,700 because the window only goes up to 10 in the Y max. So you want to make sure that your graph can at least see the 2,700. So I'm just going to put 3,000 there for now. Okay, so I hit graph there, I can see my line now going across the top. Okay. Okay. So then what we're going to do for the other part, that y is equal to 2, we're going to put the other side of this equation. So this bigger piece here is going to go on this side. So go to 1,500 bracket 1.01875 bracket to the power of 4x. You can't put a t in, you got to put your x's in there. Then you hit graph. All right. So this looks pretty good. You can actually see the intersection here. If you couldn't see the intersection, say you put an n there, the intersection would be a little bit further off this graph. You'd have to change your window and move the x max to try to find it, or zoom out. I'd like the zoom out function because it zooms out in all directions, or zooms into all directions. So you kind of mess this part up, and sometimes it makes the graph look a little squished when it shouldn't. So you can just play around with the x max until the graph fits. In this case, because we graphed the way it says over here, which is the 4t, when we solve for t, in this case the intersection here, we actually get this number in years. So t is 7 point, I don't know if we want to the nearest year or so. So 7.9 years. Because it's compounded quarterly, you can't stop at 0.9. So let's just say 8 years. He's going to save his money for 8 years in this interest to be able to buy that guitar that he wants to buy. Okay. Now, that also does bring up a good point, like how do we round these? Like I can't round it down. Usually, in these kind of questions, we usually don't round down because sometimes it doesn't make sense. You won't have enough money if I round it down by accident or to the previous quarter. So most of the time we round up to make sure that he actually has enough money in the account. All right. So let's see what else we have here. Okay, let's load this. Okay, so we're going to do the same thing for this next question here. So you invest $60,000, so that's going to be my principal amount. So $60,000 per annum. Annum is very much like annual. It happens once per year. So annum stands for year. Sometimes it says per A, or you might see something that looks like this, /A. The A stands for year. It's an annual thing, an annum. And this is compounded semi-annually. So my period, my compounding period, is semi-annual. So that means it's happening twice a year. So it's half a year. If I want to put that in there, half a year. Okay. Now it's important knowing that that's half a year. So when we get to our formula, how much will they have in 25 years? I don't have to times the 25 by 2. I could just put in my formula and say, I got my $60,000 to start off with. I have the 9% compounded per year, per year compounded semi-annually. So that means what I'm going to do with this 9% to start off with is take the 9% and divide it by 2 to get the 4.5% that you'd have for every half a year. Okay, for half a year. There's a lot of fractions of that. Okay, so I'm going to add that on to the 1. So I'm going to go 1 plus 0.045. So change to the decimal. And then my exponent, I'm going to have t being the actual number of years, not how many periods have happened, how many compounded periods have happened, divided by a half. Now, again, you're divided by a fraction. So you have to do the reciprocal. So this turns into my equation, $60,000, 1.045. Oh, I'm going to pause just 1 second. All right, so back at it here. So, I'm sorry, like this, sometimes I get stopped. Talk to some teachers, maybe a student who kind of walks in here. I have to talk to them beforehand. So you might see me stop and then talk, and I might repeat myself a few times. That's just the facts of this reality that we're in. So here I'm dividing by a half. This is going to turn into 2t. All right, so now what we can do is we can graph this graph like we did before. Oh, actually, we don't have to graph this one. We just want to know how much this is going to count by 25 here. So we're going to put in 25 in our t-spot. You can see what this equation is going to do automatically. It's going to double the 25 to a 50, which is what we kind of want to do because we're going to get compounded semi-annually in 25 years. There's 50 compounding periods. So we put this all together. Put in your calculator. Let's pull out my calculator here. So 60,000 times 1.04 to the power of 50. Okay, so in 25 years' time, $60,000, because 9% per year is quite big, $60,000 turns into $541,958. There's some sense in there. I'll just go to the nearest dollar here. So that's how much money you'll have. But quite a bit. All right, 25 years, 9% annual interest is pretty good. And just sitting there doing nothing for a lot of time. So maybe you want to suggest if you have $60,000 right now, invest it. Or maybe not in this market. Wait till the market starts rebounding, then invest it. Let's see, how much money would you need to invest now? So they're looking for the P. They want to know what's my P value. Oh, sorry, not my P value. Yeah, they're looking for the P value. And I want to have $40,000 at the end, right? So my I that we have here, so let me just scroll here, sorry. So my I, this is per day, compounded daily, so I don't have to do anything with my I, because those two things are the same thing. So my I is this. My T is just the days, right? But the thing is, this isn't days per day, this is 7 years. So how many days is 7 years? So 7 years, because that is beyond the leap years, because there's going to be a leap year in there. We're going to have to use the 365.25 days per year. 0.25 includes part of a leap year, so there will be a leap year within there. So I'm going to 365.25. So the number of days that I have here is 2,506.75 days. So I'm going to use that as my time. So we're going to separate our equation. Now we're solving for p, so I don't know what the p is, but I do know what the a is. It's 4,000. I'm going to set it up. I'm going to go 1 plus this percentage. Now this percentage is a rather small percentage. So I divide it by 100. So I got this number here. And my time. Let me just put my number in my exponent here. Okay. So let's simplify this down. So we have 4,000. We got a p that we're trying to find. This is 1.0003. And then we have 2,506.75. Okay. So it's a rather large exponent, but this is a really small percentage. So this is still a growth function. Percentage is, it's larger than 1, so it is going to grow, but it's going to grow ever so slowly. But there's a lot of periods here, a lot of compounding periods. So this number actually might end up being pretty big. So let's see what it is. So I'm going to just type all that in my calculator and see what happens. So it's 1.0003 to the power of this answer that I have here. Okay? So even with all of that, even with this small percentage and that large exponent, this ends up being 2.153 ... There's a lot of decimals there. And then we just simply divide over that number to get the p by itself. So we're going to take this 4,000, we're going to divide it by the 2.153, and we're going to get p is to be slightly less than half that number. So you would have to invest, or to start off with, in 7 years, or 7 years in the past here, oops. That's $1,857.87, or 78 cents, sorry. Yeah, that's how much you would have to invest to start off with, if you want 7 in a year. All right.